So what we're gonna have is just frequency of the injected light needs to be above some threshold frequency. Or if we're talking about the wavelengths of the light, it must be smaller than some threshold frequency. So if your frequency is smaller than the threshold frequency, no matter how big the intensity is, no matter how big your wave is, like the amplitude of your wave is, you don't have any photoelectrons ejected. Or if we put it on this figure, we can imagine we have two beams of light. So the red light has a smaller frequency, the blue light has a bigger frequency. So in this case, if the red light with a smaller frequency is used, and that is smaller than the threshold frequency, no matter how intense your wave is, you don't have any photoelectron ejected. Alternatively, if your frequency is larger than the threshold frequency, you'll get electron ejected. And we can measure the kinetic energy of the photoelectron that's being ejected. And that's our second piece of observation here. So the maximum kinetic energy of the ejected photoelectrons is directly proportional to the difference between the frequency of the light used minus the threshold frequency. And the slope is measured to be Planck constant. All right, so these are the two pieces of information you can't really explain using the classical theory, because in the classical theory, we're relating the energy with the amplitude. But in this case, the amplitude doesn't matter. What matters is the frequency of the light. And what we have, say this is my threshold frequency. And if we're measuring the kinetic energy, and on the x-axis, we have the actual frequency here. What we're expecting is before the threshold frequency, that from 0 to mu naught, we have no ejection. And after the threshold frequency, there's a linear relationship between the kinetic energy and the difference between frequency minus mu naught. And the slope there is just our Planck constant. So I'm going to use that quote again. What we say is whenever our experimental observation doesn't fit in our existing theory, scientists will update the theory. So in this case, the classical picture of light behaving as pure wave doesn't explain the experimental outcome of photoelectric experiments. So that's why Einstein came out with the new hypothesis, which is the wave-particle duality of light. So I'm just going to write it here. You don't need to copy it down because you'll have it on your textbook and the annotated notes. What we have is a light of frequency mu consists of quantas of energy. And what we have is energy of a photon, of a single photon, equals to Planck constant times the frequency of the light wave. So let's try using this new picture of photon being quantas of energy with E photon equals to h mu to rationalize what is happening in the photoelectric experiments. All right. So, firstly, an electron at the metal surface will absorb a photon of energy. Again, in this case, we have the energy of the photon equals to h mu. So depending on the frequency of the light you're using, the energy available or the energy provided by that photon is going to change. So again, we have two different scenarios. The first scenario is when your frequency is smaller than the threshold frequency. So each photon does not carry sufficient energy to excite an electron. Right? So the way to think about it is one photon is give all its energy to one electron. Depending on the frequency of the light, it may or may not have enough energy to activate that electron. So that means when our frequency of the light is smaller than the threshold frequency, we have no photoelectron ejected. And when the energy of the photon is big enough, the electron can escape and gain certain kinetic energy. So I'm going to show you a graphical representation, and let's come back to the actual graph figure and see if it makes sense. So what I'm saying here, if I just draw an energy diagram, and what we have, that's on the y-axis, that's the energy. What we have is we have certain energy in my photon. So we have E photon equals to h mu. And each photon, or just one photon, is going to transfer all its energy into one electron on the surface of your photocathode. So all of the E photon is transferred onto the photocathode. And then that electron need to pass through some threshold. And that threshold is what we call a work function, equals to Planck constant times h naught. So mu naught. Mu naught is our threshold frequency. H is our Planck constant. And this phi is a work function of the photocathode. It is one of the inherent property of any metal you can talk about. So for different metal, for different photocathodes, they might have different work function, right? So work function describes how strong your electron is binded onto that metal surface. And the work function phi equals to h mu naught, where mu naught here is our threshold frequency. So now let's just imagine our h mu is larger than h mu naught, the work function. Because of the conservation of energy, right? So now the electron has more energy than it needs. So after it escapes from the surface of the metal, it's still going to have some kind of kinetic energy. And that's what we are measuring here in the photoelectric experiment. So that kinetic energy, we call it Emax, or maximum kinetic energy. That's measurable in our photoelectric experiment. So if you write out our Emax here would equal to E photon minus the work function, which is why we have Emax is a function of h mu minus h mu naught, or the Planck constant times mu minus mu naught. All right, so go back to what we're observing in the photoelectric experiment. I'm just gonna copy this figure out, and we look at the actual observation again. What we have here, so before, when mu is smaller than mu naught, means that each photon doesn't carry enough energy to bypass that work function. So if we draw the energy diagram, right, so the work function, that's a constant. But my E photon is smaller than that work function. So for this region, we have no ejection at all. Because even if your photon is transferred all its energy into the electron at the surface of this photocathode, it still doesn't have enough energy to be ejected. It's going to remain where it is. So your photoelectrons are not ejected. They don't have any kinetic energy at all. So that's when the frequency is smaller than the threshold frequency. And when your frequency is larger than the threshold frequency, this is what we have, right? So your photon is transfer all its energy, which is h mu, to the photoelectron. It gets enough energy to be ejected from the photocathode and gains certain kinetic energy. And the relationship x, which is the y-axis we're plotting, equals to h times mu minus mu naught. All right, how are we doing here? I'm gonna pause for a little bit for questions, and then we're gonna do several example questions together. Yes?
You say photoelectron, you just mean like electron or something?
Right, so photoelectrons are specific for electrons in the photoelectric experiments. They are essentially just electrons on the metal surface of the photocathode. Other questions? Okay, all right, we're all smart enough to understand how Einstein got his Nobel Prize. And now we can look at some example questions in how to use this theory to understand or to do problems together. All right. So we're gonna do all these problems together. So let me just keep a copy available for you. If you have a piece of paper, so you can follow it. All right. So we have 3 example questions. We can do it together. The first question we read, a typical human eye will respond to light with wavelengths from 390 nanometer to 700 nanometer. Our retina only responds when the radiant energy, so how much energy the light has, will at least be 4 times 10 to the negative 17 joule. So the question asks, what is the minimum number of photons needed for our eye to see? Like how many photons we need. So to solve this problem, first let's write out what we know. What we have is that energy equals to 4 times 0, 0 times 10 to the negative 17 joules. And it is asking for minimum number of photons needed. So in order for it to have minimum number of photons, we should be expecting it to have a large frequency. All right, so think about it. If the frequency is large, we have E equals to N times H mu, right? So if your frequency is large, then the total number here, the N here, is gonna be a smaller number. So we want it to be minimum number of photons. So that's why we're talking about the maximum, lights with maximum frequency. So maximum frequency and small minimum wavelength, right? So the relationship here is C equals to frequency times lambda. So we read the question again, and we only respond to 390 nanometer to 700 nanometer. So we're talking about wavelengths with 390 nanometers. So that's the smallest wavelengths we can see. So in this case, we have lambda equals to 390 nanometer. So this part of analysis is without doing any calculation. You just look at the equation and you get an idea about what numbers to use when reading the question. Okay, so now we can do the calculation together. So we know that speed of light equals to frequency times wavelength lambda, or frequency equals to c over lambda. So maximum frequency equals to c over minimum wavelength. And do that calculation together. We plug in the speed of light. It's about 3.00 times 10 to the 8th meters second over 390 nanometer, and transfer that into meters. I always keep my units around just to make sure I'm canceling out the terms correctly. And we can calculate the maximum frequency to be 7.69 times 10 to the 14 s minus 1, or hertz. And then it becomes quite simple. We just plug in our frequency max into our energy equation. So E equals to NH mu equals to 4.00 times 10 to the negative 17 joule. Or we can rewrite N equals to E over H mu. That equals to 4.00 times 10 to the negative 17 joules over the Planck constant, 6.626 times 10 to the negative 34 joule second, and the frequency we just calculated, 7.69 times 10 to the 14 s minus 1. Here we're just checking the unit. We're talking about numbers, so all unit cancels out. And do that calculation, we get 78.6. And since we're talking about just number of photon, minimum number of photon, it needs to be an integer number. So we need to round it up. So that's gonna be 79. Numbers. And if you think about it, that's going to be a purple light because the wavelength is 390 nanometer. You might also be asked what color of the light it is. All right. So any questions before we move on? Yes.
If we're asked the color of the light, will we be given the spectrum?
Well, it's open book, so you can use you can use whatever materials you see fit. All right, so that's our first question here. Yes.
Oh, sorry. In the calculation above, where we are looking for the frequency, the max, I think if you go up a little bit more, yeah. I'm sorry. Where did you get the 10A on the right side?
10 to the 9th.
Yeah, is that 10?
Oh, that just says like 1 meter, you have 10 to the 9th nanometer. That's just converting nanometer to meters. Are you doing okay with this? Yes.
So NHD, that comes from Emax, right? You're taking the maximum energy of one electron times the amount of, or one photon.
So I guess here, when we're talking, the question is N E equals to NH mu comes from maximum energy. So you don't have to think about it this way. So when we're saying E equals to NH mu, what we're saying here is for each photon, let me just write here, it's more space. For each photon, E photon equals to H mu. So N here just tells you how many photons are there. So like 1 photon, that's h mu of energy. 2 photons, that's 2 h mu of energy. So that's the relationship. Yes?
Can you explain how you knew to use the 390?
Right, so the question is how do we actually choose the 390, not the other numbers? So what the question is asking is for the minimum of photon needed. So looking at this relationship here, right, so E equals to N times H mu. H mu is energy in each photon. We want minimum number of N, so this mu needs to be the maximum number of your frequency. You need to use the largest frequency you can get. And because the wave of light time equals to mu times lambda, so if you want largest frequency, you're looking for the smallest wavelength. So that's how it's related. We're not doing any calculation to identify that 390 nanometer here. All right? Okay. So this is one of the way you can be tested on. So the take-home message here is you want to relate the energy of a light with its frequency using the relationship, which is E photon equals to h mu, and N just tells you the number of photons available there. Okay, and now we're moving on to our second question. You can read the question when I put it down here. So what we have now is we want to use the work function. And you can be asked to calculate the maximum kinetic energy of the ejected electrons. When you have, say, a blue light is shine on there. So it's the same experiment. It's the same photoelectric experiment. Now I'm just giving you the wave function. I'm giving you the wavelengths of the light that's being used. And can you calculate the maximum kinetic energy of the ejected electrons? All right. So in this example, again, we can use, if you're not so familiar with the setup or how this equation is coming from, I recommend you just draw the energy diagram again. So what we have is E photon gives all its energy to a photoelectron. The photoelectron bypass a work function which equals to h mu naught. The mu naught is our threshold frequency, and it's gonna gain certain kinetic energy. And because of the conservation of energy, so this E photon equals to h mu, and that's where this equation comes from, right? So everything is linked here by conservation of energy. So now the question becomes easier once you understand what it is asking. You're simply plugging numbers here. It is asking us for the maximum kinetic energy, and it gives us the work function, so that's out of 5. It also gives me the wavelength of the light. So by doing calculation, we also know h mu or E photon. And we can do the calculations together here. So E photon equals to h mu, or we only have the wavelengths here, so we need to convert it using the speed of light over wavelength. And do that calculation. We get Planck constant 6.626 times 10 to the negative 34 joule second times the speed of light, 3 times 8 meter per second, over lambda, which is 450 times 10 to the negative 9. The 10 to the negative 9 comes from nanometer meters. And let's see how the energy term how the units cancel out. So meter cancel out with meter, S minus 1 cancel out with that S, and we end up with 4.41 times 10 to the negative 19 joules. And here we have joule, which is a unit for energy, and that's a sanity check that you have your calculation correct. So that's why I always keep the unit when I'm writing my equation. So we're happy because we're getting the unit for energy. So that's the energy of the photon. That's this part. And then we have our work function. The question gives the work function to be 2.10 electron volts. And we need to convert the terms here. So 1 electron volt equals to 1.60 times 10 to the negative 19 joules. So either you converted the joule into electron volt, or you convert electron volt to joule. It doesn't matter, as long as you keep the unit consistent. So what I'm gonna do here is just kinetic energy equals to that h mu term, which is 4.41 times 10 to the negative 19 joules, divided by 1.60 times 10 to the negative 19 joule per electron volts, minus 2.10 electron volts. And what we're getting is 0.66 electron volt. And that is the kinetic energy the question is asking for. All right, so the calculation is not hard, just plug in numbers, but you need to know what number you need to plug in and what's the physical meaning behind these calculations. I'm gonna pause again for any questions you may have. Yes?
Would it also be possible for us to answer it in joules instead of electron?
Yeah, you can also write it in joules instead of electron volts. So as long as your calculation is consistent, I don't really mind which unit you end up with. Yes?
Can you explain how you got E photon equals H mu equals HC over lambda?
This one?
Yeah.
All right, so the question is where we get this h mu equals hc over lambda term, right? So this one we have c equals to lambda times mu. So mu equals to c over lambda. And we plug in this mu equals to c over lambda into there. Yes. Questions? Yes?
Is the energy of the photon always equal to kinetic energy?
The energy of the photon doesn't equal to kinetic energy. So again, what we're doing here is there's a relationship between the energy of the photon, the work function, and the kinetic energy, right? So the total energy available as energy of the photon, it always equal to h mu. And that depends on how much energy are there in each photon, and what is the work function of your photocathode. You get the kinetic energy term later. Okay. Any other questions? Okay, and this is another way you can expect a question being asked on topic of photoelectric effects, right? So again, the very fundamental take-home message here is this relationship, this energy diagram. If you're not certain about what you're calculating, I highly recommend you just draw it out and figure out what's the relationship between the energy of the photon, the work function, and the kinetic energy. Okay, next up, we have one last question here. So this one is slightly peculiar. This one you can actually check your result with the formula sheet, because we're asked to calculate the Planck constant. So the question reads, when lithium is irradiated with light in a photoelectric experiment, we have the following observation. say the kinetic energy of the photoelectron being ejected is 2.935 times 10 to the negative 19 joule, when the lambda is 300 nanometer. And when you increase the light that's being used to 400 nanometer, the electron is ejected with smaller kinetic energy, which is, in this case, is 1.280 times 10 to the negative 19 joule. I didn't ask you here, but you can think about it. Why, when you have larger or longer wavelengths, the photoelectron that's being ejected has smaller kinetic energy? So just a take-home think, right? Why that's the case? You could well be asked about that in your discussion worksheet or your exam. But this question is asked you to calculate the Planck constant h. So before we get started, imagine what we have talked about before. Right, remember in that observation here, we have the kinetic energy, and let's say here is our frequency. And say this is my frequency mu. And remember, the observation is gonna be when the light is smaller than the threshold frequency, there's no ejection, and after, you'll have an ejection with slope equals to Planck constant. And we could take 2 points here. Right, so here we have Emax 1 corresponding to mu1, and Emax 2 corresponding to mu2. And in this relationship, what we already have are these points. So we know what E1 is, we know what E2 is, we know what mu1 and mu2 are. So we're just trying to use these numbers to estimate the slope, which is the Planck constant. So this is just basic algebra. What we can write is estimate Planck slope. Let's say equals to h equals to E1 minus E2 mu1 minus mu2. And we have mu equals to c over lambda again. You can do it differently, but I'm just gonna take the longer road to calculate mu1 and mu2. So mu1 equals to c over lambda 1 equals to 3 times 10 to the 8th meter per second over 300 times negative 9 meter, and equals to 1.00 times 10 to the 15. That's minus 1. Likewise, we can have mu2 equals to c over lambda 2 is 3 times 10 to the 8th meter per second, 400 times 10 to the negative 9 meter. Cancel out the terms, we get 7.50 times 10 to the 14. That's minus 1. And we use that to plug in the numbers to estimate our Planck constant. So that's h equals to, again, what we have is E1 minus E2 over frequency 1 minus frequency 2. You can plug in those numbers. 2.935 times 10 to the negative 19 joules minus 1.280 times 10 to the negative 19 joules. On the bottom, we have the frequency we just calculated. It's the 1.0 times 10 to the 15 minus 7.50. I think I write that the other way. Right, never mind. Times 10 to the 14, and it's minus 1. So I'm gonna, well, if you have a calculator, you can plug in numbers, and what we're getting is about 6.62 times 10 to the negative 34 joule second. And we all know what Planck constant is. It's about 6.626 times 10 to the 34, negative 34, and we're happy here. So I think this calls to an end of our talk for the fundamental of quantum mechanics. Last time we talked about energy quantization. Today we talk about wave-particle duality. And we see some example questions. And you can already see, right, there are different ways you can expect a question on the wave-particle duality. All right, thank you for your attention. I'm not going to be here for Friday and next Monday. We'll have Dr. Pham on Friday, Dr. Cobbler for Monday. I'll also upload my recording for the lecture as well. All right.